You have probably heard of consistent hashing, but have you ever wondered why it is designed the way it is? To explore that, I tried to build my own version once. It looked perfect until it completely broke, and that failure, that one flawed idea, is what finally made me understand the genius behind consistent hashing. So let me show you where my design went wrong and how single but subtle idea captures the true essence of consistency. And spoiler alert, it's so simple it made me question my entire design. Well, before we even get there, we have to understand what is hashing. Hashing in layman's term is a mathematical formula where we take an input, like some key, run it through a hash function, and we get a deterministic integer evenly spread across a range. Formally speaking, hash is a function which will directly give an output ranging between 0 to n. Now in a distributed system, we often use hashing to decide which server handles a key. So let's imagine we have three servers, S0, S1 and S2. The simplest mapping might look like this. Server is equal to hash of a key modulo 3. Each key maps to a number in range of 0 to 2, and that number decides its server. So in our diagram, key 0 will map to S0, key 1 will map to S1, key 2 will map to S2, key 3 will map to S2, and key 4 will map to S1. Everything looks neat until we add one more server. Now it's hash of a key modulo 4. Suddenly, almost every mapping changes. Key 0, which used to go to S0, now goes to S1. Key 4 jumps from S1 to S0. Roughly 75% of the key moved, causing total chaos. Now that's the rehashing problem. Every time we add or remove a node, we invalidate most of our old mappings. And in distributed caches or CDNs, that means data shuffling, cold caches, and massive imbalances. So I thought there has to be a smarter way. I wanted something stable and predictable. A system where adding a new server wouldn't require touching everything. So I came up with an idea. Each server gets a fixed identity, defined mathematically. For n servers, the server I get an identity as a linear equation, where identity will be equal to total number of servers into any kind of natural number range plus the server index. Now each key gets hashed into an integer, and if that hash matches the server identity, we assign it there, moving clockwise around the ring. So key 0 has a hash of 609159, which fits in 2n plus 1 range, which will make S1 the server assigned to key 0. Now key 2 has a hash of 459722, which fits in 2n, which will basically make S0 the server for key 2. Now in this way we will assign all the keys to certain servers. When I add a new server, I just don't test the existing ones. I simply compute its identity using the total new count, where identity will be now equal to the total number of new server count into n plus the new updated position. So S0 and S1 will keep their old spot, and now the new S2 will take its new position. Like in our case, it will be 3n plus 1. Then I simply traverse through the ring clockwise, and any key whose hash now fits the new identity moves to S2. Simple, right? Visually, it looks perfect, only a few keys moved, and I thought finally I built a scalable hashing, except for the fact that it broke horribly. So where it broke? You see, when the number of server changes, the spacing between the identity start to break down. It's no longer uniform. Each time a new server joins, the problem of where to place it and how it will affect the entire system becomes even messier. Even if I add just a new one server, the entire identity pattern shifted. That means every key has to be searched, recalculated, and reassigned across these servers. A full reiteration in reshuffling cycle might be required every time. I even tried it patching with wraparound logic, optimizing it, but the mat itself wasn't stable. It kept depending on how many servers existed and changed accordingly to how each server is positioned exactly. So my predictable design turned out to be too dynamic. The keys weren't evenly spread, some servers were overloaded, others were barely used. That's when it hit me. What I built wasn't consistent hashing, it was just a broken imitation of it. So now you might be wondering how consistent hashing actually works. The real deal starts with one single but genius idea. The hash space should never be dependent on total number of servers. So let's define a fixed circular hash space, say from number 0 to 2 to the power 32 minus 1. Then we will hash both the servers and the keys. Now each key will move clockwise until it finds the next server on the ring, and that's its owner. So for example, server 0 will hash to position 0, server 1 will go to 25,555 and server 2 will go to 516003. Now hashing a key will lead to different position, key 0 to 609159, which will land somewhere after S2, which will wrap it around to S0. Now key 1 will go to 44167, which will be around somewhere between S0 and S1, which will belong to S1. So now key 2 will go somewhere around S1 and S2, will now wrap around to S2. Key 3 will go to S2 and key 4 will go to S1. Now each server owns a segment of the circle and each key will lie somewhere in that segment. That's why it will belong to that particular server. Now what happens when you add or remove a server? Only the key that falls in that corresponding segment move. So when S2 will be removed, it key slide to the next clockwise server, say S0, without touching anything else. Mathematically, it's just one of every n keys will be remapped on average. You see, the other big difference from our version is that we don't even try to iterate through all the keys. Just the keys that have been assigned to a particular segment will be remapped. But you might ask, there's one big problem. What if one server hash land on a huge empty section? It will get overloaded. Well, the fix is easy, virtual nodes. Instead of giving each server one point at a ring, we give it hundreds with each of different hash. So a single physical server appears on multiple random points, spreading its ownership evenly across the ring. And now the hash space is naturally balanced. No manual tuning, no global reshuffling. And when a node fails, its virtual node segment gets smoothly redistributed to the remaining ones. Simply, this means that the key will be reassigned to a server whose virtual node it encounters first when moving clockwise, and that's the simple principle behind the virtual node and consistent hashing. When my design failed, I finally understood what makes consistent hashing truly elegant. It's not about clever math or formulas, it's about restraint. The restraint to only touch those keys that are needed to be reassigned. Instead of rebuilding everything when the world changes like what we did in my version, just touch the bare minimum necessary. And that one idea quietly powers some of the biggest systems on earth. And as someone who tried to outsmart it once, I can tell you, it's simple, but it earns our respect. So that's it, my first deep dive. And honestly, making this video drained me a lot more than I thought it would. Anyways, I'm really hungry. Making this video took a toll on me, so I think I will grab something to eat and probably get some more sleep.